There we go. Hooray. Alrighty, so today let's go ahead and here, let me move this giant red mic out of the way. Let's start with doing some reaction practice. How about we do classic reaction here? Let's see if we can't figure out what the products are going to be of this. And let's also do what's one that we could do with here? How about this? How about we do... Yes. Okay, let's do those two. Good morning. So let's go ahead and figure out the products of these two reactions. So first thing, of course, did we have class on Tuesday, like tomorrow? Or last week? Last week I sent out an email that we were not meeting on Tuesday. And I had also posted it on Discord. So last week, no, we did not have Tuesday class. Yeah, you should have gotten an email on Monday night that there was no class on Tuesday. Okay, so yeah, let's go ahead and figure out the products of these. What do we think we're gonna get? Hush, little dude. Little monster. What do we think we're gonna get here for the first one? I know these will take a minute since we're not necessarily used to them. Let's just remember what our ions are, of course. Indeed. The one thing, Kenji, with your barium nitrate, that one is not charge balanced properly. What are we missing there, Kenji? Well, that's weird. Did anybody else not get the email? Okay, well, so Kenji, I know you're here. Did you get an email last week that I said the class was canceled? Or rather, I wasn't going to stream on Tuesday? By the way, this is what we're missing. Okay, Lamanda got it. Okay, well, who knows? Maybe one of them got lost. Okay, cool. Alrighty, so yeah, the other thing, Kenji, since barium is 2+, we're gonna need 2 nitrates for that. So that's the only thing that's lost. Okay, awesome. Nice job, Kenji. Both Maya. All right, next one's a little bit tricky here. By the way, of course, this first one was a double displacement, right? What kind of reaction is the second one here? And then let's see if we can't figure out the products. Yes, this one is going to be a single one, right? Beautiful job. Absolutely right. So Lamonda has replaced the nickel with zinc and has charge balanced appropriately. Remember, zinc always takes a 2 plus charge. And so sulfate is 2 minus, so that's why they cancel each other out there. So that is excellent, excellent job there. And again, of course, it does not matter which order you put these. You could put nickel first or zinc sulfate, either way. One thing that just to note, because we're not introducing the activity series, yes, so Kenji, if this reaction worked, it would say that zinc is more reactive than nickel. Yes, that would be one thing we would learn there. Again, I'm not necessarily referencing the activity series, so maybe it's not, but we'll pretend it is. So remember, for this class, it'll always work. Okay, so we're not going to necessarily have to worry about predicting which one's more reactive. Oops. One thing I do want to note, though, if you're doing single replacement, with a metal with variable charge, so normally, again, you would be able to use a chart or something to see what would happen. But for us, we don't have to worry about that. We are going to assume a charge of +2. So luckily for us, we are just going to make this assumption that it's going to form a 2 plus charge. So if we were to use iron instead of zinc for this one, we would assume that it would be iron 2 that would come out in the product. Zinc, of course, does not have a variable charge, so it has to be +2. But if it is a transition metal or something that has a variable charge, assume it's going to be +2 in a single replacement reaction. So, for example, we can do that one. Let's say we had iron plus, oh my gosh, go away, software update. Let's see, what shall we react with iron today? So we're going to assume here that iron will be in the +2 state. So it would form FeCl2. and you would just kick out your cobalt at the end. So that's what this part means here. So anytime we're going to have a transition metal that could do multiple charges, for a single replacement, we're going to just assume +2. And we'll just have that as a blanket across the board for variable charged metals. Anything that has a fixed charge, like aluminum, would always still be 3+. So this does not apply to fixed charge things, only variable charge things. Okay? How about we do this one? No, let's not do that one. That one would be too complicated, I think. How about we do... Yeah, let's do this one. Let's do this one. Silver always is +1. So that is not a variable charge metal. So remember, going back to our, let's see. Is this the one? No. Is this the, yeah. So if we look at, I don't know. If we look at this thing from way back when, we can see all of our fixed charge metals or non-metals on this, right? So anything that's not got one thing on it, including any of these other things that aren't listed. So let's see if I can write on this nicely. Okay, so notice we have, I forgot zinc. All of these things we already know the charge of for our metals. So those ones will still be whatever those charges are. Anything that's not circled here, however, could be variable charge, and as a result, we're going to assume +2. So anything else that you're going to see, assume +2. The ones that are fixed like this, we're not going to worry about. Those will always still be their same charges. That one is in the handout section. It's also on Canvas. So it's right here in handout. Handouts under summary of ions. Okay. So if you're looking at your thing, handouts is right below general. So it's right there, but again, it is on Canvas as well. Okay. Alrighty, let's go ahead and do this sulfuric acid and potassium hydroxide. What type of reaction is this one going to be? By the way, of course, this one was single replacement, but we didn't have to predict the products. That was an example. So close, Kenji. One thing missing there again. That's one of them. And this one is almost complete. Yeah. That's the one. Man, the software update is just so aggressive. So notice, just so we all see here, that's where the water came from. So anytime we have H plus and OH minus coming together, that will make water. Alrighty, how are these feeling? So don't forget there is plenty of... no, this one is a double displacement reaction. Decomposition would be one thing turning into multiple things. So this we have two things, two ionic compounds. Decomposition would be something more like if we had something like this. That would be a decomposition reaction where we're breaking it into multiple things. So, but yeah, don't worry, I'm not going to ask you to predict decomposition products like that. So this one would be decomp. Alrighty, well, let's start adding a few things in here. So we're going to start Kenji's favorite topic, which is balancing the equations. So let's go ahead and let's look at that top one there. I'm just going to rewrite it down here. Alrighty, so we know matter cannot be created or destroyed, right? That is a fundamental law that we have in chemistry, law of conservation of matter, or mass rather. So we can't just get rid of things out of nowhere. So that tells us whatever we put in, whatever atoms we put in, has to be the same as the atoms that come out. So that means essentially we need to have the same number of every element on the reactant side of the reaction as well as on the product side of the reaction. And so I like to just kind of set up a table with reactants and products, and we just write out all the elements that we have in our, not Cl2, in our reaction. So in this particular reaction, we have three elements here. We have iron, cobalt, and chlorine. And it's a good idea to tally out how many we have on each side. So on the reactant side, we have 1 iron, 1 cobalt, 3 chlorines. That's all just looking at the compounds there. And if we see here, we have 1 iron on the product side, 1 cobalt on the product side, and 2 chlorines in there. So, looking at these numbers, it looks like iron and cobalt are technically already balanced. So, however, we see the chlorine here, there's a difference. Left side has 3, right side has 2. Once your reaction is here, we're never going to add any more components. Like, we can't just say, haha, no problem, let's just throw a chlorine at the end. No. Does not work that way. Can't just throw on an extra random element or something. That would be very nice, right? Too easy, Lawanda. So, but no. Once we have our reaction, those are the only components we're going to use. So, what we would need to do is we're going to add more of those components as necessary so that it does become balanced. So, if we were to add a second, or you know what, let's just do it this way. We can see here that if one side is 3, the other side is 2, what's the kind of happy ground that would allow them to both be the same? We're kind of looking at that least common multiple idea again here. Same with like charge balancing. We're going to want to make both of these chlorines into 6. And in that way, we'll have balanced both sides. So if we look at it, on the right, we get 2 chlorines at a time. On the left, we get 3 chlorines at a time based on our compounds. And so the best way to make them balance each other out is to have 6 chlorines, because that way both compounds could equally contribute 6 chlorines. So if we want these chlorines to be 6, we're going to have to adjust our components here. How many cobalt 3 chlorides would we need to make 6 total chlorine atoms? Keeping in mind that each one gives 3, of course. We're going to need 2 of them, right? As a result, we'll have 6 chlorines now on our reactant side. Notice, however, we also have changed our cobalt. That one is now 2 also. Okay, Kenji's gone ahead and done the whole thing, but let's do this step by step for those who have not practiced it over the weekend, which is awesome, by the way. Very nice. So, same thing on the other side. How many iron 2 chlorides are we going to need? We're going to need 3 of them to get to that magic number of 6 in this case. That is going to end up changing our number of irons. So now let's go back and rebalance iron. So if we have 1 iron on the left, 3 on the right, we're going to need to make it such that the left side, the reactant side, has 3. And we're going to need to make it so our product side has 2 cobalts. And so as a result, we will have balanced this equation. And by looking at it, we can see all the numbers are the same on both sides. We have 3 irons on both sides. We have 2 cobalts on both sides. We have 6 chlorines on both sides. I guess I should put this as balancing equations or something. This is like a little subheading. Alrighty. Let's go ahead and do that other example. We had sulfuric acid plus potassium hydroxide turning into water plus potassium sulfate. So we're finally now at that stage where we're going to deal with those pesky coefficients and subscripts. So remember that we don't ever see K2+, that 2 is there to balance the sulfate. Now we're finally going to be able to address that in here using this idea of balancing. So when you're balancing also, it's always a good idea to not mess up your polyatomic ions. Nobody click this random person's thing. Of course, so if we look at the first one, we have H plus and sulfate. On the other one, we have potassium and hydroxide. I don't know why I'm putting the charges on this. So remember, hydroxide is a polyatomic ion, right? There's a spammer there. Just ignore it. This has not been an issue, so I will ignore it as well. Okay. Remembering that water is HOH. So we'll just kind of remember that as well. Okay, so how many H's do we have that are not part of hydroxides on the left? Which sadly is written R for reactants. We have 2 of them, right? We have 2 H pluses. On the right, how many H's do we have that are not part of OH? We just have 1 of them, right? Sulfates, if we're looking at sulfates, right now we have 1 on the left, 1 on the right. Remember, if there were multiple sulfates, you'd use parentheses, so I do not see any parentheses here, so we don't have more than 1. Potassium's on the left, we have 1. Potassium's on the right, we have 2. And now we can deal with hydroxides. So it looks like on the left we have 1 hydroxide. On the right we have 1 hydroxide. So it doesn't really matter necessarily which when you decide to balance first. I usually just go top to bottom. Usually is the easiest. In combustion reactions, we're going to see it will become slightly more tough, but going top to bottom would still work. So if we want to balance out the H's that are not part of hydroxide, I see our least common multiple there would be 2. So that tells us we need to have 2 waters, which is also going to bump up our hydroxides to 2. Looking at sulfate, that's already balanced, so we can keep on going. Potassiums, we have 1 on the left, 2 on the right. So we will want to put a 2 in front of the potassium hydroxide to fix that potassium problem. And notice also we will also double our hydroxides. And looking at these numbers, now everything is balanced. Easy. Any questions on that one? Alrighty. How about another one? I'll let you guys do this. What are the products going to be? Let's figure out the products first, and then let's balance it. By the way, I will post 100 balancing practice problems for you, with the answers, of course, so you can have as much fun as you want practicing this. Let's see. Balancing equations, yes. Alrighty, so while you are doing that, I'll post this for you. Okay, that's good. I mean, you can do as many as you want. You can do 0 of them. You can do 3 of them. You can do 78 of them. Totally your choice. I shall wait. Looking at the periodic table, okay. I am curious what you're looking at the periodic table, or at what you're looking, but we'll see. Looks good, Lamonda. Kenji, do not look at the screen. What type of reaction was this, Lamonda? Or anyone else? Yes, indeed. Ah, Kenji has even put some react states of matter on there. Yes, you would see it is going to be a precipitate, but right now, Kenji, we're not worrying about the states of matter. So we'll be talking about that once we're done with balancing. So probably towards the end of class today, we'll worry about that. The one thing on your yeah, exactly. So that's why he wanted the extra time, I guess. Just note, Kenji, you should have 2 phosphates because calcium is a +2 charge. Alrighty, let's go ahead and balance this. Yeah, this was double displacement for whoever said it. Yes. And of course we can tell that because there are 2 ionic compounds reacting together. Okay. So we have our reactant side, our product side, we have calcium, we have chlorine, we have sodium, and we have phosphate. Let's see if I can rescue that. Not really. Okay. Calcium's on the reactants, we have 1. Products, we have 3. Chlorine's on the... Yeah, well, we're going to do net ionic equations tomorrow. Those are exciting. Sodiums, we have 3. Sodiums, we have 1 on the right. Phosphates, we have 1 and 2. So let's go ahead and fix calcium. Again, I usually just go straight down the list. And then always double check at the end, because sometimes if you're doing stuff, you might change one of the others. So it is always a good idea to double check at the end that everything is balanced. So if we need to make calcium have 3, we can do that. No. Notice that also brings our chlorines to 6 by doing that. So now we have to fix chlorines on the right. So if we need them to be equal, we're going to have to put 6 there, which is going to change our sodium as well. And so if we need the sodiums to become 6, we're going to need to put the coefficient of 2 there. The balancing act. And notice that also changes our phosphate to 2. And so hooray, it is balanced now. Any questions on this one? Okay. Let's do one of Kenji's problems now. What type of reaction is this one? It's interesting. My glasses have started like reflecting the screen more and more. Yes, Kenji, look what it is. I already gave you the example. This one should not have a fraction, though. The next one will. I'll show you another way to avoid the fraction thingy, but let's do this one first. This one will be easier. What's the type of reaction? This is combustion. Yep, absolutely. Which means our products are combustion, of course, being the easiest one to figure out what the products are, right? All combustion products, of course, just, yeah, CO2 and H2O, exactly. Alrighty. So, it begins. Carbons, we have 3 and 1. Hydrogens, we have 8 and 2. Oxygens, we have 2 and 2 plus 1. Notice that now we have oxygen as part of two compounds here. We have it as part of carbon dioxide and water. So that makes oxygen a bit complicated, doesn't it? I'm just going to go ahead and write 3, by the way. But we'll have to remember that we have to look at both carbon dioxide and water when we're balancing oxygen. So the way I mean, since this order already has oxygen on the bottom, what? You said decomposition? I don't see you saying that anywhere on this, but that's okay. Alrighty, so looking at this, we can change carbon. However, notice that will change our oxygen. So now we in fact have 7 oxygens. We have 6 from carbon dioxide. We have 1 from water, so that's 7 overall. Looking at hydrogens, what is going to be our least common multiple there? We could actually just make this into 8. Right, since 2 divides into 8, that's 4, right? So we can put a 4 here. So now we have 10 oxygens. And how are we going to make 2 turn into 10? We're going to multiply by 5, right? So we stick a 5 in there. And lo and behold, we have balanced our equation. So the only tricky part here is remembering that oxygen is present in both compounds in the products. So we just have to make sure that we account for that. Sometimes, however, with these pesky combustion reactions, sometimes bad things happen. Let me make this a little bit more obvious. 10, yes. Yikes, let's look at this one. We have 4, 10, and 2. On the product side, we have 1 carbon, 2 hydrogens, 3 oxygens. Alrighty, and so if we want carbon to be balanced, we would need to make this one into a 4. That would put our oxygens at 9. We would have 8 from carbon dioxide, 1 from water. Looking at the hydrogens, we would need to make that 10 by putting a 5 there, yes? If we think we now have 8 plus 5, I can do this, 13. Oops, I'm sorry, I'll keep that there. We now have 13 oxygens. Oh, but we have a problem now. Problem is, we have oxygen, which always comes as an even number on the left, and we have an odd number of oxygens on the right. Well, normally, yes, we could just say, let's just do the least common multiple. That would be 26. We'll make the oxygens 26. It would be easy. However, it may not be obvious to you, do you need to increase CO2 or water? Because there's 2 products with it. 2 ways to address this. Easiest way is to use a fraction, but apparently that upsets Kenji quite a bit. Notice if we put a fraction as our coefficient, we could get 13 oxygens out of this, and we would be able to balance it that way. This is option 1. Putting a fraction as a coefficient would allow us to get past this troublesome oxygen molecule. So that's one way to do it. And as we can see here, we don't normally put fractions in our equations, do we? We like to have everything as kind of the lowest integer values. So what we would probably do to get rid of that thing, we would multiply the whole equation by 2. And that would get rid of our fraction. If we do that, we end up getting just multiplying all of our coefficients by 2 would get us this reaction at the end. And as we can, if we were to just go ahead and look at this, we would have 8, 20, 26, same thing on both sides. So that is one way to go about doing it, is putting the fraction and then unfortunately this is going to be a big part of 111 if you end up taking that. So combustion analysis. So yeah, that would be nice. So that's one thing you could do. But I have another secret for you that would avoid this problem. Hooray, by the way. Secret is Kenji, I love my word problems. We'll have to see, though. A lot of these are going to be like, what's the coefficient of this? What's the state of this? Blah, blah, blah. We could, instead of worrying about the potential existence of fractions, we could just double everything at the start. Oops. If you want what on the exam? Oh, I see. I don't quite recall saying, do you want word problems or not? Alrighty, so let's try it this way. Let's try doubling it at the start. So if we double everything, we start with 8 carbons, 4 carbons, 20 hydrogens, 4 hydrogens, 4 oxygens, and lo and behold, we have an even number of oxygens this time. Last Wednesday, I said no word problems. I mean, these typically aren't going to be word problems. I mean, I don't see how I would structure one as a word problem, at least right now. But you can definitely bet you're going to get a question saying, what's the coefficient of oxygen going to be in this reaction? Or coefficient of carbon dioxide or whatever. Alrighty, so let's look at this, by the way. So if we need our carbons to be 8 now, we're going to have to make this into an 8. If we do that, we're going to have 16 plus 2, that is 18 oxygens. To balance out the hydrogens, we're going to need 20 of those. So if we need 20 hydrogens, that's going to mean we need 10 waters. And that's going to change our oxygen as well. We're going to end up with 26. We have 16 from carbon dioxide, 10 from water, 26 in total. And we can figure out how to get this thing to 26 by changing that coefficient to 13. Each oxygen is 2, 13 of them would give us 26 oxygens. So that would be the other option, is you can just multiply everything by 2 at the start. And as you can see here, we did not run into any problem with an even number or an odd number of oxygens. So you see here, all the numbers that we had were all even because we doubled everything. So you can do this for any combustion reaction. Indeed, miraculous. Just one thing to note, though. You always want to double check at the end. So, if we look at this one, we did this reaction before. This reaction we did before. Notice something special about all these guys. These ones are all divisible by 2, so we should always report the lowest integers we can. So we should keep this as these coefficients. Well, technically, yes, the top one is correct. We always like to have the lowest possible integer values. So we do have that for this one. Notice we have an odd number. We can't divide all of these by 2. So we're okay with this one. But if we did the doubling at the start for this one, we would want to double check that we still have the lowest ratios possible. If we did double at the start for this propane problem, you would end up with 2, 10, 6, and 8. All of those are even, so you would just want to reduce them at the end. So that's the note here. So always reduce coefficients to the smallest possible integers. Okay, so that's the takeaway there. So yes, by doubling this thing, we're getting rid of the odd problem, but just double check that if you do double it, that you don't end up with something that needs to be reduced. Okay, so that's the kind of trade-off there. So by avoiding fractions, you just have to double check at the end. That's your payment for using the cheating way. Not cheating. Okay, so if ever you get coefficients that are not the smallest possible integers, you'll want to make them the smallest ones. Alrighty. So it is now time to talk about state of matter in a chemical reaction. So we have 4 of those. We did talk about these earlier. Okay. We're going to also want to note what the state of matter is going to be for our products that are given in our reaction. Liquid is honestly the easiest one. There's usually only one product that's a liquid. There might be 2 depending, but typically liquid is the easiest one for us. A lot of them will be aqueous, some of them will be solids, some will be gases. We're going to learn all of the different ones for this. And thankfully, we already looked at a lot of this last chapter. We remember that soluble ionic compounds will be aqueous if any reactant is aqueous. So, if any reactant is aqueous, anything that is soluble will also be aqueous if it's a product. So, thinking back to that, we would probably want to refer to our solubility rules, right? We remember that anything with, one of these guys, so that's, remember, just refreshing your solubility rules. Anything with these ones will be soluble, right? We also saw that we could do the same thing with our halides. I'm, just refreshing it, so I'm not going to write out everything. And the last one that we had for soluble things was going to be the sulfates. And all these guys as well. Alrighty, so blue things were soluble, red things were not. Anything that is not on this list, we're going to assume is insoluble as well. So you will probably want to review your solubility rules for tomorrow, just since we're pretty much out of time for today, so we're not going to get too much practice in right now. So we're going to see that anything insoluble will be a solid in the reaction. So that would be something like this one. We know that silver chloride should be insoluble, and as a result, it would be solid. The ones for the reactants, you'll be given the state of matter, so you do not need to figure that out for yourself. But the products, you will always be asked to figure out what the state of matter is. So if we look at sodium nitrate there, that of course should be aqueous, right? It has sodium and it has nitrate, both of which will always be soluble. So we would mark our solid one, the insoluble one, with an S to note that it would be solid in a reaction. And so we'll see evidence of this tomorrow, and where we continue on with this sort of thing. Alrighty, luckily for us, water and bromine are liquids in double displacement or single replacement reactions. So for example, that would produce NaCl, which would be aqueous because it's got sodium in it. And we would have water as the other product. Water is a liquid when it's produced in a double displacement or single replacement reaction. Alrighty, so gases, we're going to have 4 of them. We're going to have to see those tomorrow, I suppose, because I don't want to go over time. So we'll continue gases tomorrow. It would be a very good idea to review your solubility rules, these ones here, just to make sure that the more familiar you are with them, the faster you'll be able to apply the knowledge. All right, I guess I can just throw this one on here. Just remember, so Lamanda, anything that has one of those 6 at the top is always soluble no matter what the other part of it is. So sodium phosphate would be soluble, sodium carbonate would be soluble, sodium whatever, throw in your own polyatomic ion there, should always be soluble. So I don't want to say yes to your question right away, because sulfates are typically soluble unless they're paired with one of these 6 things. And then halides are also soluble unless they're put with one of those 3 things. So normally we would expect a chloride to be soluble. Iron 3 chloride is soluble. Cobalt 3 chloride is soluble. Zinc chloride is soluble. But silver chloride is not. However, silver nitrate is soluble. Silver acetate is soluble. So it's not so simple as the sentence you've described there. So basically, the easiest way to get around it is anything that's in blue here is going to be soluble. If you look at the second 2, the chloride one and then the sulfate one, those just have a few exceptions. So the exceptions are in red. If those ones happen to be with a red ion, then Yeah, so definitely just go over them. That'll behoove you. Yeah, cool. And then, so I guess I didn't say it. Remember, acids are aqueous. That's something we learned way back when. Acids always come with that aqueous label, so we'll be good there. Okay, looks like we're out of time today. So tomorrow we will continue on with states of matter in our chemical reactions, and we're going to start talking about net ionic equations, and maybe we'll do redox reactions. We'll see. Alrighty. Take care, everyone. Oh, wait, don't go. Let me show you on Canvas where I put the thing. Okay, Canvas, where are we? Okay, so if you go to this, I guess, let me slow down. Homepage for Canvas, yes? We go down to balancing equations here, right under, and you can see here we have this whole thing. You can, so apparently Maya wants to do 100 of them. You can go ahead and do this, and you would get all these reactions to try and play around with. So you'll be able to say, okay, this is a, apparently I can't click it. Maybe I need to have it in a new tab. Whatever. Apparently this part does, oh, there we go. Oh, it's just not showing up. That's weird. I see it here. There is a drop down that comes when you click it, but it's not showing for whatever reason on my screen here. And you would just put in your answers for the coefficients. You would click grade it, and it would give you the right answer as well as the type of reaction. So this is a very useful tool for you guys to practice with. Again, you can do as many as you want. This is totally on you. Hey, look, I got one right by not doing anything. So, yeah. Alrighty, cool. So have fun with that. Alrighty. So now, take care. See you tomorrow.